This is a lesson on naming compounds and the mole. Not quite the same thing, but we'll get there. Binary compounds contain two different types of atoms. Two different types of atoms. CaF2 is the formula for calcium fluoride. U before O and fluoride, it's not fluoride. So you just off the periodic table, whatever's in front, and then your ending is IDE, because of the binary compound. If you have cobalt 2 fluoride, you want to write the formula. Cobalt 2 has a charge of 2. Fluoride is F with a charge of 1. And if they're not the same and they can't be reduced, you crisscross. So the charge of 2 on the cobalt goes down here with the F, and the charge of 1, absolute value, goes down with the O. So COF is the formula for cobalt 2 fluoride. This is a review from last year. On page 62 in your book, or whatever page I assign, is a listing of polyatomic ions. A couple of changes and unique things that you should know about. First of all, back to the hydrides, binary compounds. If it ends with H, if you have LiH, that means the H is a -1 charge, and that's called lithium hydride. So hydrogen with the ide at the end. Not hydroxide, hydride. So that's kind of a weird exception, something new from last year. Now on page, the page with all the polyatomic ions on it, you have all sorts of different listings of things. There's many different types. One of them is mercury 1. Looks like this. It has a charge of 2, but there are 2 of them, so each one gets 1. It's a diatomic ion. So that's kind of a weird critter that you gotta know. Other things on here, there are many of them. Many of these you can just memorize. Some of these you have. In the past, I had you do 7, like ammonia, nitrate, sulfate, hydroxide, phosphate, carbonate. These you should be all familiar with. There are some on here that you haven't seen before. There's a general rule. Let's look at the chlorates. ClO3- is chlorate. Chlorate is the standard or the typical one that you'll find. Now if you add one more oxygen to that, the charge stays the same. That's perchlorate. Per means one more oxygen than normal. Then you can have ClO2-, which is chlorite. If it ends with ITE, that means it's one less oxygen than the standard. And you can have ClO-, which is bleach, hypochlorite. hypoblankite has 2 less oxygen. So if you memorize that general span, you can handle many of the problems on this page. Hypo means under, so it's under the under one. So that's one way of remembering which one it is. Is it hyper or hypo? Hypo goes under. Per means hyper, so that's too many. You know, like ooh. Other things that are common, you can have carbonate, and you can throw a hydrogen in front of that and make it hydrogen carbonate. They have bicarbonate, but I don't prefer that. I prefer hydrogen carbonate. It's really easy to do with memorization stuff. Other things that you might notice, CN minus cyanide, SCN, they might have it in a different order, is thiocyanate. Other ones on here, permanganate. We are going to do labs with permanganate, so it's kind of important for you to know what that is. Chromate. And dichromate. We use these frequently when we talk about reduction and oxidation reactions. And oxalate. We do a lab where we're going to make an oxalate. So you should know that. So these are the things that you should know. As far as using them in your writing, they're the same as before. ONaHSO4. Na, sodium. HSO4 is hydrogen sulfate. Iron 3 of SO3. Charge on Fe. Oh crap! Did it wrong. Iron 3. Let's make it phosphite. It's not in your list, but you know the rules, so you can figure out what it is. Iron 3, Fe, charge of 3. Phosphate is PO4, so phosphite is PO3, and its charge is 3. 3 plus 3 minus cancels, and you're done. Molecular compounds use prefixes. They are in your book. I'll give you the page number, or you can look them up. Prefixes, mono, di, tri, tetra. You just don't start with mono, like CO2 is carbon dioxide, not monocarbon dioxide. Dioxide. Acids. If you have no oxygen in the formula, it's hydroblankic acid. Hydro is the hydrogen part for the acid. The blank is your atom. So if it's HBr, that would be hydrobromic acid. If it's H2SE, that would be hydroselenic acid. And you can go the opposite way too. If you have hydrosulfuric acid. H, no oxygen, sulfur. So it's H's and sulfurs, 1 plus, 2 minus, crisscross, H2S. That's if there's no oxygen. If there is oxygen, and we're only going to do the ones with the 8 and the ite. So if it's with oxygen, if it's like sulfate or sulfite, the 8 would go to blank ic acid. The ite would be blank us acid. So if you have HClO2, CO2 is chlorite, so this would be chlorous acid. Phosphoric acid. Acid starts with an H. Phosphoric, it's an ic, so it's an 8, so that's phosphate. 1 plus, 3 minus, so you got an H3PO4. And now on to atomic masses. A mass spectrometer, it looks kind of like one of those Crookes tubes the J.J. Thomson used. What you do is you ionize an atom sample and you send it through these giant magnets. This is a pair of giant magnets, and it creates a magnetic stream, and it will pull different isotopes. The more neutrons you have, the closer it falls. The less neutrons you have, the farther it is. And this is a sensitive thing, so it can register, like this is 10% of the total, this is 50% of the total, this is 40% of the total. And the distance down, you can measure how much AMU that is. Farther down, the less AMU it is. So it's a reverse scale. So heavier atoms would be up here. Lighter atoms would be down here. So you can measure out the distances and come up with a weighted average. So the AMU, or atomic mass unit, is the weighted average of the atoms in a natural mix of atoms in nature. So it's a weighted average of the atoms in a sample found in nature. If you go to mercury, you have more ionization, so you might have different percentages. So oxygen might not be 16, oxygen's AMU might be 15.8. It won't be a whole big jump, but it could be different according to where you are. By definition, we set carbon 12 as equal to 12 AMU. We don't use hydrogen 1 as 1 AMU because it's so light. Carbon 12 is heavier, so you can mess with it and deal with it. And so that's how you do that. If you want to find out what the average is, if it's, say this was 35, so it's 10% of 35. This is farther down, so it's a little bit lighter, so it's plus 50% of 37, say, plus, this is farther down yet, 40% of 39, just to keep the pattern going. And if you take those up and average them, that would be your mass of this compound that you have. Mole is 6.02214 times 10 to the 23rd atoms is the number. That's the more drawn out. Last year we did 6.02. This year we're going to do 6.022. So we want to go to 4 significant digits on this. It's the number of atoms needed to change the atom's AMU to grams. So if you have say you have a compound that's, or some sample that's 35, an atom's 35 AMU. If you have 6.02, if you multiply that by 6.022 times 10 to the 23rd, you'll end up with 35 grams. So it's just a conversion factor between grams and atomic mass units. And this is how you can convert between atoms to grams, and grams to atoms. It's not too difficult. Say you have 1.5 moles of oxygen. How many atoms is that? Conversion, 6.022 times 10 to the 23rd over 1 mole. Molecules. I think I said atoms before. So that's how you do that. Molar mass is the same thing, except you have to add up all of the atoms in the compound. Oh, my fault. It's the same as the atomic mass, except for formula units. Yeah, that's right. I said it right. So if you have water, H2O, that's 2 times 1 plus 16 is 18. So that's 18 AMU. That's 18 grams per mole. Either one works. And you can do conversions again with this. Same thing as the other one. Checking. And that completes this lesson on naming and atomic mass.